Okay, and the last talk, before eventually the break comes and then the last keynote, is Emanuel.
Thank you, everyone. My name is Emanuel Lima, and I'm going to talk to you guys about cadCAD.jl, modeling library for generalized dynamical systems. So first of all, just a bit about me. I am a senior research software engineer at Block Science, an R&D firm from the United States. And I'm also the lead engineer for the cadCAD project. That is the software I'm about to show you guys. So here's my email and my GitHub accounts if you guys want to reach after the presentation. So first things first, what is cadCAD.jl? So cadCAD.jl is a library to orchestrate and simulate trajectories of generalized dynamical systems. It stands for Complex Adaptive Dynamics Computer-Aided Design. It's just a mouthful, but you guys are going to get a clearer picture of what the library does in a moment. Basically, it's an open source framework for generalized dynamical systems. It's a generalization of the idea, of the theory of a dynamical system. We already have a legacy version of the library that has been developed in Python that implements a subset of that theory of GDS, meaning that it does simulations based on a subset of that mathematical framework. We are working right now on a reference implementation in Python that actually implements the whole of GDS, all possible simulations that could be done in GDS. And we are also, hence why I'm here, working on a performance implementation in Julia that also implements the whole of GDS as well. So what is a dynamical system? So very basically, dynamical system is a representation of an observed phenomena that includes a state, which is basically the snapshot of a system, and includes rules about the time evolution of that system. And it comes in many flavors. So the evolution of a dynamical system, for example, can be entirely deterministic, or it can be subject to non-deterministic influences, to randomness, that is external or internal of the system. Typical, quote-unquote, dynamical system evolves a state x over time t according to a certain function, and that function can vary over time. So either the attributes of that state or the function that actually evolves the system can vary over time, can be random. So the state transition of that system would be a function of the previous steps, of the previous state. So that's how the time evolution of a system would occur. And it can be continuous or discrete. So that's the very brief overview of the regular dynamical systems as we learn in universities. But in cadCAD, we simulate generalized dynamical systems. And the difference is that a GDS does not have to just talk about numbers, just talk about very contrived examples that are numeric in nature. A GDS can have a state represented by a generic data structure. So for example, in this picture, the data structure we're talking about have a lot of different types. And this is where a language with a good type system such as Julia comes in. For example, this particle here has types, strings, floats. It could be integers, it could be user-defined types, and it could also be nested. So, for example, this particle data structure has another data structure as one of its types inside of its own data structure. That is, for example, the Cartesian plane. So that's basically the main difference between GDS and a regular dynamical system on the context of computer simulations we're talking about here. A brief rundown of GDS from a mathematical standpoint. So basically a GDS is a pair, h and x, where the h from x to x, as we talked about on the regular dynamical systems slides, is a state transition map, and x is a state on a state space. So x is the big X, capital X, is actually the state space. So this is just to say formally that GDS is a bunch of states that belong to the space of all possible states, future and past, and a function x that is basically the composition of all of the functions that time evolutes the system. And a GDS is that pair that is the function and the space. And when the function is applied over and over to elements of that space, we have a trajectory. So the trajectory is basically the list, or the vector, for example, of all the states that were produced during a simulation. Right? But more specifically about cadCAD's model of computation. So we saw here that a generalized dynamical system, we must have a space and states inside of that space and a function that evolutes the states. Those functions on cadCAD's model of computations, we call them blocks. So those blocks are basically small units of logic that accept specifically some kind of input and output a specific kind of output. So here on this picture, you can see, for example, if you focus just on this process 1 here. On this process 1, you can see that it has a yellow D and a green B on the box. This means that, it's just to clarify that process 1 is a block or is a function that only accepts data of type D and only outputs data of type B, right? So by doing that, I can ensure that I can make very complex logic, very complex kinds of state transformation by concatenating, like Legos, different pieces of blocks, different logics that can transformate my system. This is going to become a bit clearer when I get to the actual example. But for example here, process 1 accepts data of type D and outputs data of type B. So after process 1, the data that comes out of process 1 is a data of type B, so it has to be put inside another block that accepts type B. If I try to put it on a block that accepts another kind of type, so the library would raise an error. So the pipeline of all the blocks concatenated in a coherent fashion is what we were calling here on this formalized notion the H, right? So this whole pipeline would be run for each time step of the simulation. We can have, for example, on this process 2 here, blocks that are endogenous. So for example, they don't accept any data. They don't have any data coming in, but they output a data, in this case, of type E that is red, for example. So it would output this data, and another block would have to accept it, in this case, the block process 3. And the logic itself inside of those blocks is just regular Julia code. So what is important from cadCAD's point of view is that the data that is flowing from one point to the other of the pipeline is always type safe. It's always the correct kind of types that is coming in and coming out. If you take a look at process 5, when process 5 finishes digesting its data, finishes its logic, it outputs type D, yellow D, and that is fed back into the beginning of the pipeline again to process 1. So because we have this closed loop here, then we actually have a simulation. Because the next state that is produced, the next step on the simulation is always based on the previous step. So that's how we have a time evolution of a generalized dynamical system. And the importance of using block diagrams becomes clear when we look at this picture here. So there are these 3 properties that a block diagram gives us when doing simulations in cadCAD. So first, it's tiering. I can take a look at this picture here, and I can zoom in and tear it apart and examine the individual logics of each of those processes. So I can look at just process 1, process 2, 3, 4, or 5, and take a look what kind of data is coming in, coming out, and the logic it's producing. I can tear it all apart and look at it individually, but I could also pick up another pipeline, another set of blocks, and just concatenate it if the kind of data that is outputted from the other pipeline is the same as it is inputted on this pipeline. So I can tear a pipeline of blocks into smaller blocks, I can analyze the individual blocks, and I can link them back together. So I can zoom in and zoom out as I want during the modeling of a system. So basically, so why did we in the first place started cadCAD.jl? So it was our experience that when doing model-based systems engineering, the systems engineers, they were using expensive proprietary software for modeling like MATLAB. And cadCAD is basically an open source alternative to MATLAB on a model-based systems engineering context that plugs very easily into other SciML frameworks and libraries, but also on the greater Julia data science environment. So you can start a simulation in cadCAD, and then you can use it to train a model, or you can use the resulting trajectory and plot it using the usual Julia libraries, because in the end, the trajectory is a regular Julia data structure. Right? Internally, it's basically just compact structs in memory. And the main selling point is the schema. Basically, the schema is the shape of all the types on this data structure, the data structure that represents my world, the world that I am simulating. That is completely arbitrary. I can put any kind of types that I want. They can be high-performance types. They can be types that I defined. They can be strings. If, for example, my world is just strings that I evolve over time according to certain rules, my schema, my space, can be just strings. So it doesn't matter. cadCAD is agnostic to all of that. So the use cases for cadCAD that we envision is basically to engineer and validate complex systems, so to do design digital twins, to do model-based data-driven decision-making, and also live health monitoring and forecasts, as in operational digital twins. So these are basically the biggest use cases we are envisioning for cadCAD for the future. So I'm going to just present a very simple example of a prey-predator simulation on cadCAD on how it would be written as a model in cadCAD. This model right now, it can't be run completely from top to bottom because cadCAD is a work in progress. The library is in an alpha state and is still being heavily developed. But basically, this is the API as it is designed today. So this picture just demonstrates how the simulation is going to behave, so the actions of the simulation. So we have those first four light gray, I guess, boxes, the predator births, prey births, predator deaths, and prey deaths. And then each of those boxes are blocks. So each of those boxes are like the ones I drew here, are small and atomic units of logic that digest data from a certain type and spits data on another type. So we have those functions here, those blocks here, and then we have the blocks join naturals, natural causes, and hunt. Basically, the light gray, the light green boxes say that how the populations of predators and prey will change on an environment based on natural causes, let's say, like a lightning or an accident, a disease, or whatever. And births, just births. Join naturals, as you will see in a moment, is a block that doesn't have a logic by itself. It just concatenates all the data that comes out of the green boxes into one data structure. So this is just to demonstrate that a block can have a logic that doesn't actually digest the data that comes in, but just reshapes it. And natural causes is basically just actually updating the population of preys and predators based on the natural causes of the green boxes. And the hunt block here at the end is actually how the prey population is going to decrease based on predators eating them, basically. And the simulation loop is from natural causes to hunt, and then back to natural causes to hunt, and then you see the time evolution of the predator and prey population. So basically, the first thing that a modeler would do, he would declare all the spaces that capture the simulations I'm trying to do. So we can do this with a macro. That population, we have to declare that it's basically an identifier together with a type. On the syntax of cadCAD.jl, it must have a type because, as we said, like those types are basically the contract that must be obeyed about the data that is coming in and coming out of a block. So I'm going to say that the prey population is an unsigned integer because I don't want like a negative population. Predator population is also an unsigned integer. And I asked like the Julia runtime to choose the size for me based on where it's running. So no size annotation. Also, I created another space called delta population. And that delta population is an integer, so it can be negative. So that delta is basically just the amount of change of a population during the simulation. And the joined delta space is a data structure that is going to be concatenated on this join naturals block. It's going to be a bit clearer later on. Here, I'm just setting the parameters of the simulation. Those parameters are just regular Julia named tuples. I'm just putting like a rate of births for preys, a rate of birth for predators, a rate of death for both of them as well, some constants, and this simparams here is just the configuration of how I want to run this simulation. So I want the number of steps to be 1,000, so I want the simulation to run that pipeline, the whole pipeline, I mean this whole pipeline, to run 1,000 times. I want the parameters of that simulation to be these that I declared just before. And I want it to run one time, because what I can do is to actually create a list of trajectories. So that would be a matrix. So I can run that simulation a number of times, change the params slightly, and to see how slight change on the parameters can change the graph of the evolution of the predators and the preys. So the blocks in cadCAD.jl are just regular Julia functions, but they have this specific signature. So they have to have a domain, and that domain must be a space. They must have a codomain, and that codomain must also be a space. And optionally, you can have parameters. So these parameters that I pass here are is the named tuple that I defined here. The logic that goes inside of those functions can be any. It's up to the modeler. But what I'm doing here is basically just randomly choosing how many predators are going to be born, preys as well, and how many predators and preys are going to die of natural causes. The domain is the shape or the size, the space of the data that comes in, and the codomain of the data that comes out. Here, I'm just joining all of the delta population spaces that came from these blocks here. So if you see the codomain of this block, or the data that comes out, is a delta population. And a delta population is just one integer. So I want to join them all together by this block here on a codomain that is a joined delta. If you go here, the joined delta is just a bunch of delta populations, 4 delta populations, right? So I join these 4 functions here, 4 blocks here, on just one data structure. And that is exactly what this yellow block here is doing. So by joining them, I can just say that this block is digesting, is actually bringing together a lot of delta populations. You can see that the domain of this block is multiple, and its codomain is just one. It's this joined delta. And finally, I have the 2 blocks that actually do the simulation. Is first the natural causes. So it accepts population as a domain, and a joint delta also as a domain. And as a codomain, it returns population. So it accepts a population, the delta of that population, or how that population is going to change, and then gives back the population updated. That population is updated by the natural causes of that environment. And then the hunt block will accept the populations as the domain and give back a population as a codomain, meaning it will pick up the population that comes already updated from natural causes, is going to do a hunt, and then give back a population updated with the results of that hunt. If you see the logic, I picked up something that's very simple, just for an example's sake. So it basically says for every hunt, there is a 5% decrease on the size of a prey. But I mean, the logic is agnostic and be any kind of Julia logic, because at the end, a block is just a regular Julia function with this signature. And then I define the initial state. So I'm going to say that initially, the state of my population is 1,000 preys and 15 predators. I write this pipeline. So the pipeline is basically a DSL that we are devising to say basically how this figure is becoming this string. And I then ask for the cadCAD engine to run, and this run produces this trajectory. And that's basically it. So cadCAD is, I don't have more time, but cadCAD is work in progress. We would like if you guys could join us. And thank you.
Thank you for the talk. Any questions?
Thank you. Thank you for the presentation. I have a simple question. I noticed that despite being a dynamical system, it seems like it's not limited to dynamical systems that can be expressed in an analytical formula, like a math formula, right? It can be anything really, right?
Yes.
But would I be able to just write a custom function that does, I don't know, like solves the wave equation or something like that, and add that as a I forgot the name that you use to define these blocks. Can I just write any function and compose a simulation using that?
Yes, yes. It's completely agnostic to what you can do. So you can write a block that does anything on any kind of shape, any kind of space. So it's completely up to you. Yeah.
Thank you.
Thanks. So your framework that you presented, I consider it agent-based modeling with the additional restriction that you also have to declare a pipeline. That's how I understood at least the concept of the generalized dynamical system. And at least the simulation you presented, I know I could be doing with an agent-based modeling library. So now my question is, what are the scenarios or in which situations would I prefer using this framework of an agent-based modeling library?
Because I think that this very simple example, yes, it could be done on agent-based modeling library, but there are others that wouldn't be so great, at least in my opinion. Like, for example, I could, on those pipelines here, I believe make pipelines that are like very complex that the current agent-based modeling libraries wouldn't be able to do, as far as I know, or it would be very complex to do. And also, when I'm doing the modeling, cadCAD allows me to do a lot of stuff on those data structures, on the spaces, to create further spaces that I haven't seen another SciML library doing. I could be wrong, of course, but I could, for example, do Cartesian products and start from a data structure and create lots of other data structures afterwards. And I can, like I put here, I can zoom in, zoom out on the pipelines, and I can create very different pipelines by focusing on small pipelines and then making the pipelines reusable. So in the end, you make a pipeline that is basically a library, and we are doing a final pipeline. Your final pipeline is going to be just the import or the include of several other pipelines. And those pipelines can be parts of them running parallel and so on.
Thanks. In Julia, the agent-based modeling library, agents.jl, is not part of SciML. And perhaps you could check it out and compare there more concretely, because at least so far I could not imagine something that I couldn't do with this library. I can totally appreciate that I could do this easier with this library, but it would be good to know what are the pros and cons so that the users can know better or be better informed which one they can choose for which type of application. But thanks a lot, though.
Actually, I have a question. Do you know how? First of all, do you know the workflow management languages like KNIME and stuff, which also have kind of these blocks that you can move around and then shuffle data through?
Yeah, I think I have seen them. Yeah.
How does it compare?
Those languages, I don't think that they do the exact same thing that cadCAD does, that is picking up the data structure with data and operating on them and creating a trajectories of various other data structures. I mean, the trajectory itself, that's basically what cadCAD does. I don't know that they do that, so I think.
Okay. And do you have the interface, like the user interface, is it nowadays text-based, or do you have like a GUI?
So it's text-based nowadays, but the idea is to be able to create like that kind of picture, like to compile down diagrams into the pipeline string automatically. So, but right now the user would have to write the string according to a specific DSL.
Okay. Other questions? If not, then this was your last talk before the final events. So have a nice JuliaCon and see you tomorrow at the hackathon. And let's thank our speaker again.